All right. I think we're rolling. Um, well, I think this is our last lecture, unfortunately, at least for the semester, um, and maybe for some of you just in general if you're graduating this semester. And so, just couple of reminders: you have homework due on the 12th, okay, and and lab 5 due on the 16th. And on the 13th, I'm going to release the homework solutions and provide you your final exam. And the final exam will be in the same format you had before, where it'll be take home, open note, open book, open lecture, whatever. And we'll do that, and then your final exam will be due on the 16th. So that'll give you 2 or 3 days to do the final exam. The format of the final exam will be very much similar to the midterm. Uh, it'll be a little bit longer than the midterm, just because normally my exams are designed to fit inside a 2 hour block of time. So, but again, because it's take home, you can take as much time as you'd like, and hopefully you're not spending too much time on the exam, because I know you all have a lot of other things to work on in this class and probably in your other classes. Um, yeah, and as a result of all of this piling up, because next week is finals week. Actually, I don't know if finals week officially starts today, being Saturday, or if it's next week that it actually starts. But we won't do lecture or anything. Uh, I was debating whether to do like a sort of just a optional lecture, to finish some of the material, and depending on how far we get today, I might do that, where you can watch it if you want. It doesn't None of the material that that I cover in these optional lectures will be on the exam, so um, but we'll see. You all are very busy, I'm sure, and I will be as well, trying to get all this together. So, I mean, at the end of the day, I'm pretty happy with what we've covered so far. So, all right. Well, anyway, it's a lovely Saturday morning, so hopefully you all are staying healthy and happy, and we're going to continue our discussion on virtual memory. So, if you remember last time, we introduced virtual memory, and it's one of the oldest concepts in computer design, and essentially it gets its roots from the days when main memory was not as large as the programs demanded. We didn't have enough main memory. Our programs required, in order to actually do useful things. Our programs required a lot more memory, because remember, back in the early days of computing, we were in the hundreds of kilobytes of memory if we were lucky, and that was even for very large, expensive supercomputers. And so virtual memory provided an automatic mechanism for moving data between main memory and uh, and uh, disk. And well, of course, they didn't really call it necessarily disk back then, because actually uh, they called it secondary memory. You had your primary memory and your secondary memory, and your secondary memory was actually in the early days, it was stored on big drums, still using similar concepts to how modern magnetic hard drive storage works today, but with big drums. And so virtual memory provided an elegant solution for that. And then once we got to the point where we had enough memory to pretty much run a single program, then we started using virtual memory to allow us to run multiple programs. Okay, and so it provides a protection mechanism for each program, and also the kernel. So virtual memory protects programs from each other. So each each process has its own virtual address space, and other processes cannot access data inside that virtual address space unless it's explicitly shared. And then the operating system is protected from user programs because the operating system has its own virtual address um, mapping, and of course the hardware provides protection mechanisms that allow privileged access. Okay, so very simple mechanism is just the hardware keeps track of a bit that indicates whether the processor is in user or kernel mode. Okay, and towards the end of this lecture, we'll talk about how we actually um, control that bit, how that bit's actually controlled. But when you're executing in user mode, you can only access memory in your user space, your specific user space. And then, as we'll talk about later in lecture, there's an application space ID that allows you to keep track, allows the processor to keep track of where your user space actually is. And then if you want to do privileged level things, you have to invoke a system call, which then uh, puts the processor into kernel mode. And then in kernel mode, it can then access kernel space and other privileged instructions. So anyway, it's kind of interesting how all those mechanisms work together, and of course, all of this works in concert with the operating system. You could think of this hardware. This hardware is really mechanisms, providing mechanisms for the operating system, and the operating system is what manages all this. In fact, I don't know if I mentioned this last time, but the operating system is really what manages virtual memory. Okay, contrast that with our hardware managed caches, where the refill logic and all of that is all handled in hardware, and the operating system really doesn't have to do much in terms of caching. But for virtual memory, the operating system is an integral part of the virtual memory system, and the hardware provides the mechanisms that the operating system needs to actually carry out that virtual memory. So again, from a high level, we take an application's virtual address space and we break it up into these pages. Okay, and they're typically 4 kilobytes in size, but like Linux allows support for large pages, and so there's trade-offs between having the granularity at which you break your memory space up and you know, for smaller programs, really they do better with smaller pages. Larger programs, very large programs that are processing gigabytes of data, they do well with large pages, and so you can actually um, specify the page size in well, the operating system can adjust the page size. Okay, and the hardware has to provide a mechanism for that as well, and we'll talk about that in a little bit. And so as we mentioned, these pages can either be stored in physical address space, so in main memory, or they can be stored on disk. Okay, and so again, that concept dates back to the early days of computing, and this was really the primary driver for virtual memory, was that we can't fit our entire virtual address space in physical memory. We actually have to uh, store some of the pages out on disk, and then if you go to access a particular page and it's not in the physical memory, then the operating system will swap a page, and so it just like we talked about in cache, it'll figure out what's the least recently used page, and it'll write that out to disk, and then pull the requested page into main memory. And that's a very slow operation. You're talking millions of clock cycles because you're going out to disk. And then, like I say, we would actually extend this diagram to handle multiple virtual address spaces. So I'm just gonna draw the top half of another virtual address space so you can visualize that. And again, those pages could be mapped either in um, in physical memory, or oh, there's an available page. Look at that, it's up there. Let's go grab it. Okay, for this example, there it is. Okay, so you would either map in disk or physical address space. And so, of course, if you look at your activity monitor or task manager, it's activity monitor in Mac OS and it's task manager in Windows, and then in Linux you can use top or PS, and that'll show you all the different processes running. You're going to see that there's hundreds, if not thousands of processes. Maybe thousands is a bit of an exaggeration, but definitely hundreds of processes running, even just on a simple PC platform, and of course the server world is even more so. But all these processes are running, and some of them that are idle, that honestly they're probably stowed away. The pages for idle processes are probably stowed away at disk. But one thing is today we are certainly not lacking RAM, even though the density of DRAM has slowed down significantly. We still end up with computer systems that have more than adequate amounts of RAM. And so, so really, even on this machine little tablet, I bet you only about half of the physical address space is even being used. So, oh, and another thing to point out on disk, when we talk about, so disk is called swap space, and I think I've got a slide that discusses this a little bit more. Um, you actually don't want to enable swap space for a device that has a solid state drive. In other words, that uses flash as the secondary store. Okay. The reason and this was mentioned earlier. One of the students pointed out that that flash has a you know flash wears. It has a maximum number of write cycles. And so if you set up a Linux system on a solid state drive, and you go ahead and map in swap space to that solid state drive, you can actually cause problems and wear that solid state drive out. So like this tablet here probably doesn't even have swap space enabled. Okay, so in that case, you can't really write out to disk. But hey, this little guy has 8 gigs of RAM, and that's more than enough for it, right? Even running Windows 10 operating system. So now, a server with large amounts of magnetic storage and potentially running many processes will in fact use swap space. So anyway, okay. So again, I talked about this. Each process has its own virtual address space, okay? And the beautiful thing about that is that allows our programmers to lay out their memory in the same way for every program. And really, you've seen this before. Okay, well, I went out and retrieved the my blank PDF slides. I realized that I had already queued up what I wanted to show you. So I had talked about last time, I'd kind of alluded to the fact that we have this concept of user space and kernel space, and then within the kernel space, there's different sections. And it's interesting that I can only find this diagram in one book. And you go out onto the web and you search, and maybe my searches just aren't any good, but I cannot find this diagram anywhere. And I don't understand this because everybody should be studying this and should understand how memory is laid out in a Linux system. Well, everybody that's a computer engineer, that is. Okay? But I'm just not finding that. I even went and looked at my Linux device drivers book and my Understanding the Linux kernel book, and I could not find a nice simple diagram like this. But this diagram is taken from the CMIPS run book, which, if you want to know anything about MIPS and Linux and how they work together, that CMIPS run book is gold. And in fact, at one point it was selling for like $150 or $200, and it's just a little book. It was just short supplied, and then they started producing the book again, I think, and the price went down. Anyway, it's referenced on in my syllabus, and I think you can find PDF copies online. All I know is I searched for a digital copy of what I wanted to explain, and I found one, but it turns out it's pulled from that CMIS Run book. So anyway, this right here. Oh, you know what? I can't draw on this thing, I don't think. Oh no. Well, yeah, I can, kind of. Okay, here we go. Perfect. Let me put this to a pen. That'll be fine. Okay, cool. This is I'm using a built-in photo viewer from Windows. So hey, that's awesome. So okay, so the top half is kernel space. Okay, so kernel. Let's see. Oh, I see. I can only draw on a small section. Okay, I'm sorry I wasn't more prepared for this, but I'm just going to have to describe it. So address region starting at 0x at 8 and followed by 7 zeros, okay, that area up there is kernel space, okay? Then you can see kseg 0, kseg 1, and kseg 2, okay? And then down below that is useg, and that's user space. So, and if you see, they say as seen by thread group only. And so what that means is that a thread group is a process, by the way. I don't know why they didn't use the word process, but that is what a process is. A process can have multiple threads. This was confusing for me early on in my computer engineering days. Is what's the difference between a thread and a process? And so a process has its own single view of virtual address space. So it has its own user space. Okay. And so we identify that user space with the old days it was called an application space ID. Nowadays it's called a process ID. And it may be operating system dependent too as to what they call it. I know in Linux they call it a process ID, and so a PID. And so every process has its own user space. Okay. Now you can have multiple threads within a process, especially in today's multi-core era. It's very common to have a program that has many threads. Now, of course, you can have a program that might have multiple processes, but usually when I use the term program and process synonymously. Okay, especially small programs that us normal folk write. So within a process, you can have multiple threads, and each of those threads have the same view of this virtual address space, and that's why you can see as seen by a thread group only. So any thread working within that process has access to this virtual address space and has that view. Okay? So then for every process that is running on your system, it has its own virtual address space, okay, and its own user space. Now, the upper half of the address range, so this is a 32-bit processor, so that means this is a 4 gigabyte address space. Okay, so the upper 2 gigabytes is dedicated to the kernel, and every thread has or process has this same view, okay? So every process has the same view of kernel space. Now, keep in mind that kernel space is privileged access, and you actually have to be in kernel mode to access that upper half of the address space. And you know, back in the early days when I was getting into computers and 32-bit processors were a big deal, and we were starting to get to the point where we could actually exceed 2 gigabytes and 4 gigabytes of RAM, gigabytes. And I was always confused as to why on a 4 gigabyte system do I only have 2 gigabytes of RAM for use for my program, and now of course it makes perfect sense because the other 2 gigabytes of address space is dedicated to the kernel. And of course this was designed back in the this is a MIPS and Linux sort of design back in the early days of computing, or at least of personal computing. So you're talking, like the early 80s and whatnot. And of course, Linux didn't come about till the early 90s, but you know, it's loosely based on Unix, and Unix does something similar to this. But anyway, back in at that time, having 4 GB of memory was just unheard of, right? Except for the very high performance computing sector. And of course now, I mean, we had to go to larger address spaces to support more than 4 gigs of RAM. Okay, so anyway, that's a little bit of a tangent, but um, so yeah, every thread, every process has the same view of kernel space. Okay, so because there's only one kernel, but there's multiple user spaces. Okay, and I want to come back to this diagram in a little bit um, when I have some slides on that talk about handling exceptions and all of that. Notice that the exception entry point is right here at 0x8 followed by many zeros, okay? And that's in kseg 0, okay? And we'll talk about that in a bit. But anyway, okay, so back to where I actually was going with this diagram is that every process has its own view of its own user space, and but every process can set up its user space in the exact same way, and this is very common. At the very top of the user space is the stack, and it grows downward. Okay, and then somewhere in kind of in the middle of user space you have the heap, and it grows up towards the stack, and then you have this vast open of space here. Let me see if I can draw in here. Yeah, right here. Hopefully you can see that. It's not all that dark, but I think I probably could play with the transparency. No, that's the size. Okay, whatever, that works. So that circle is open space. Okay, that's available space for the available virtual space for the program. Okay, and then you have at the very bottom you have your main program. Okay, so that's your text section, and so um, that has your well, it's your text and data section. So it has instructions and data, and they're not interleaved. They're you know, basically you go as far as you need for instructions, and then above that you have your data. Okay, that's usually the way it goes. Is the instructions are at the very bottom of the address space, and then next is your data. Oh, and then you know, this is okay. Dynamic linked libraries. This is another huge benefit of virtual memory. Okay, and that's that. Every process can then share libraries. So shared libraries are a big advantage of virtual memory. And so what's neat about this is and I really need to go to my whiteboard for this. So let's go to the whiteboard. Okay, here's our whiteboard. So this is process. Okay, I'm gonna call this process 0. Okay, and then this is process 1. Okay, and process 0 and process 1 will have a handful of libraries that they share. Okay, this is their user spaces. Okay, and so but each process, you know, it's a different program, has probably a different function and everything, and so it actually might have a different um, you know, a different uh, size of text and data section, and that's what this is, text and data. We call instructions text for some reason. That's just pretty common, you'll see. So text data. Okay, text data. So if you notice, process 1 is a little bit bigger, okay, than process 0. And then process 0 is going to have some linked libraries. And so like printf, I'm just going to put printf here. Okay, now printf really wouldn't take up this much space, but this is just one of the many uh, functions that you might share. And so what's cool about this, okay, about virtual memory, is that there's only one um, copy of printf stored in physical memory. but there's different mappings of that same uh, library for each different process. Okay, so I didn't provide enough space. I'm going to make a little bit of space here. Okay. Okay. And I'm going to put, so these are, remember, on the right and left you have your virtual address space. This is physical memory. Okay. And printf's going to be broken up into multiple pages. Okay. And so I'm going to draw this here. Hopefully I don't confuse the hell out of you. And remember, these shared library, these pages can be mapped into any real location in physical memory. Okay, and so one more and then you get the point here. But look at this. We have two different virtual address spaces and they're sharing memory. And specifically they're sharing a shared library, okay, which contains printf among other things, right? And so these shared libraries like printf map to different virtual or are in different virtual address spaces, okay? And within those address spaces, they're really at different virtual addresses. Notice the process 1, the shared libraries are higher up in the address space than in process 0. But the pages within those libraries map to the exact same location in physical memory. So now with virtual memory, we each program can have its own view of memory, which we already talked about, and within its view of memory, it has its own view of these shared libraries. But these libraries, as the name implies, they're shared, and so their address they map to the same physical address space. Okay, so now we can more efficiently develop programs, and they can share these libraries, and now those libraries only take up one location in physical memory. Okay. If you compiled your code to not use a shared library, it would basically compile printf into your program, and then each program would do that. Each program would then store a copy of the same library. Okay, so these are dynamic shared libraries. They're also called dynamic linked libraries and DLL files. You all probably heard of DLL files dealing with Windows. That is a dynamic linked library. That is a library file, and it's shared amongst multiple programs. Okay. Anyway, that's another big advantage of virtual memory. Okay. All right, and again, protection. Process 0 can't access process 1's memory except for the shared libraries. But those are generally read only, and so it's not like like process 0 can negatively affect process 1. Okay. Now, if process 0 and process 1 did want to share memory, the virtual memory system can facilitate that. And it would look like, there would be a chunk of data somewhere here, and they would then map, of course, to the same physical address block, like that. Okay? All right. So again, we divide our virtual address space up into pages. You can adjust the page size. Operating systems and the hardware have to support this, but a lot of times they can support larger page sizes in the megabytes of size, actually. 4 kilobytes is typical for a Linux system. I don't know a hell of a lot about the inner workings of the Windows operating system. I assume they use 4 kilobyte pages because 4 kilobyte pages was sort of standardized in the hardware. We're going to talk about some hardware mechanisms that make virtual memory actually practical, and as you're going to see that sort of fixes what the operating system can do. So the hardware mechanisms that we build into our processor to support virtual memory limit page sizes and things like that. So I believe Windows is probably using 4 kilobyte pages. Okay, so we break the virtual address up into two parts. We have a page offset, okay, and a virtual page number. And then the virtual page number gets translated to a physical page number. So the physical address has two parts: the page offset and the physical page number. And oh, good, I was hoping I had a diagram because I was about to go to the whiteboard if I didn't. So here we go. So our this is a 32-bit address space, so it's a 32-bit processor. But then look at this. It actually only has 29 bits, okay, of physical address space. So this would be an example of a processor that it's probably an embedded processor that is 32 bits, but it's not filling out the entire 4 gigabyte address space. In fact, how big is this? Let's see. It's 1 gigabyte because it's 30 bits of physical address space, and 2 to the 30 is 2 to the 10 times 2 to the 10 times 2 to the 10. 2 to the 10 is 1024. So 1024, that's a kilobyte, times 1024, that's a megabyte, times 1024 is a gigabyte. So this is a processor that has a 32-bit processor, but only has a 1 gigabyte of physical address space. Okay, and so we have our break right here and here. They break at the same point, and notice they break at 12 bits. What is 2 to the 12? 2 to the 12 is 4 kilobytes. So our page offset is 12 bits. And again, this is byte addressable memory, so the 12 bits allows us to address within a page. Okay. And again, this is the address that we talked about, you know, like your program counter or the address that's computed from the ALU and then feeds into the memory. But then when it's presented to the memory system breaks the address up in this way. Okay? And I know this may be getting a little confusing because you were like, well, wait a minute, we broke up addresses to handle caching. Well, in a few slides, I'm going to show you how virtual memory and caching are integrated. They're actually very tightly knit pieces of hardware. Okay, and I'll show you. There's a nice diagram that shows how the virtual memory system integrates within the caching system. Okay. Okay, so the page offset needs no translation. Okay, so that just goes straight from virtual to physical address space. But then now the virtual page number, which is the upper bits of our address, okay, that then has to be translated, and that gets translated into a physical page number, and that's how we then transition from virtual to physical memory. The processor sees virtual memory. That's what it sees. But then the memory hierarchy then translates that into physical memory, okay? And then the operating system maintains this virtual memory, okay? So the operating system has to maintain this translation somehow. So we're going to talk about how this translation happens. Look at that. How does this translation happen? Well, we have a page table, and a lot of you may have heard of this term already, but the operating system maintains a page table for every process. And that page table provides this mapping, this translation from virtual page number to physical page number. Okay? It's a ginormous table, megabytes in size, for each process. Okay? So each process has its own page table pointed to by a page table register. The page table register is a mechanism inside the hardware that allows easy access to this page table. And so every process has its own page table because every process has its own virtual address space. And in fact, the kernel has its own page table because the kernel has its own address space. And every process shares that address space when in kernel mode, of course. Okay? And so the page table is indexed by the virtual page number. So this virtual page number is used to look up the physical page number in this table. Okay? So if you can think about it, you could naively make a page table as just a giant array of translation. Okay? And you take the virtual page number along with this page table register value in the page table register. The page table register is your base to the page table, and then the virtual page number is your index into that page, or the offset into that page table, and then that allows you to then look up an entry, and the entry in there is your physical page number. Okay? Now, that's a naive way of doing it, a single level page table, and that's the way early MIPS processors were designed to only support single level page tables. But we actually, modern processors like the Linux operating system, or modern operating systems like the Linux OS, actually use um, multi-level page tables. Okay, we'll talk about that in a minute. Okay, so again, the page table is indexed by the virtual page number. Okay. So here's a nice little diagram that shows exactly what I was talking about. So again, the page offset does not need translation, so that just gets directly transferred over into the physical address. We use the page table register to point to the top of our page table, and then we use the virtual page number to index into the table. The entry in the table, there's a valid bit, and then there's the physical page number. And the valid bit tells us whether that particular page is actually in memory. If the valid bit is 0, it means that we need to go retrieve that page from disk. Okay, so if it's 1, it's in memory. If it's 0, it means we need to retrieve it from disk. A little bit, there's a subtle difference there between how we use the valid bit in virtual memory versus caching. Okay. The valid bit indicated that the cache line was invalid. This valid bit doesn't indicate that that particular page entry is invalid. It actually just indicates that it's not in that page that the physical page number is addressing is not actually in main memory. Okay, which I guess in the end does mean that this entry is invalid. Come to think of it, now that I think about it, it does actually mean this entry is invalid because there is no physical page number if the particular page that you're looking for is not in memory. So what it's going to do is it's going to go, the operating system is going to be invoked, and the operating system is going to use its least recently used algorithm to figure out which page in physical memory is the least recently used and should be evicted, and it's going to write that out to disk, and then it's going to go and read in the demanded page, and then it'll go ahead and update the page table to then point to where that page is in memory. Okay, so actually the valid bit, come to think of it, the valid bit does do almost exactly what your caching valid bit does. Okay, the page table can get quite large. Let's just do some quick math here. If we have a 32-bit address space, which by the way, 32-bit address space was like so 1990s, okay? I mean, nowadays we have 64-bit processors that can support usually up to about 48-bit address space, okay? I think the i7 is a 48-bit address space, but we'll gradually see more and more bits being used for address as time goes on. But I mean, we're never going to, at least not in my lifetime, are we going to get to 64 bits of address space? Because if you do the math, that's astronomically large. Okay, even a 32-bit address space. Okay, if we have 4 kilobyte pages, okay, we would need 2 to the 20. Okay, or 1 million page table entries. Okay, and so. Because if you have a 32-bit address space and you have, well, let's go back to, this is our 32-bit address space, right? Our page offset is 12, whoops, our page offset is 12 bits, okay, to allow us to address anything inside our 4 kilobyte page. So then the remaining bits, which is 20 bits, is then allocated to our virtual um, page number, which means that if we're using that to index our table, then our table has 2 to the 20 entries. Okay, so 2 to the 20 entries, which is a 1024 times 1024, not quite a million, right? A little bit more than a million entries. And then if each entry was 32 bits in size, which that's typical, okay, a page table entry is going to be a word, okay, which if we go back here, okay, we need to store 30 in this example. We need to store 30 bits and then a valid bit. So we need to store well, no, not 30. We have our page offset. We store 18 bits and then a valid bit. But of course, we're just going to round it off to 32. So we're going to, and then there's actually some other protection bits like read, write, executable, all of those different bits that help with our protection mechanism, shared and things like that. There's some bits for sharing memory. They'll be stored in there as well. So we just say, hey, each page table entry consumes 32 bits, okay, or a word. Well, so if we figure that out, that's going to be 4 megabytes of space. Okay, 4 megabytes because 4 words per page table entry. Or wait a minute, I'm getting confused here. Uh, 4 bytes per page table entry. Okay, and then it's about a million. It's 1024 times 1024 page table entries. So that ends up equating 4 megabytes. So we're saying that each process would require 4 megabytes just to store the page table. Okay. Now you may be wondering, well, where's the page table stored? Well, it's stored in kernel space. So the page tables for each user space is stored in kernel space. Okay, and it's stored in the kernel virtual memory address space. I can't make this shit up. Yeah, that's what happens. Let's go back to our diagram here. Okay, so we have our kernel space, and we have up here. Okay, right here is um, our kseg2, which is the kernel's mapped region. Okay, and that's where the page tables for the user processes is stored. Okay, and that is in the kernel's virtual address space. Okay, so there's going to be page tables that map to page table entries. It's kind of neat. So in fact, now is a good time for me to talk a little bit more about kernel space. So I talked about the user space and how it can be laid out. Let's talk about these 3 sections of kernel space. So we've divided kernel space into kseg 0, 1, and 2. So what do they mean? Okay, so if you see off to the left, they have little descriptors. So kseg 0 is kernel, it's cached and unmapped. Okay, so cached means that space goes through the cache. We know what that means now because we've seen how cache works. And by the way, the kseg the user space is mapped. Okay, mapped and cached. Okay, so mapped means that it uses this virtual memory system to map virtual page numbers to physical page numbers. And cached means that it goes through the cache. So user space is both cached and mapped. But and in kernel space, kseg 2 is cached and mapped. Okay. But kseg 0 is cached but not mapped. And so there actually is a rudimentary virtual to physical mapping, but it's fixed. Okay, so kseg 0 does not use a page table. Okay, kseg 0, whenever you're in kseg 0, there is a very trivial translation from virtual to physical. Okay, and so it's still within virtual address space, but it's a very trivial translation. Okay, notice that exceptions vector to that region of memory. Okay, and that'll be important per our discussion later on in the lecture here. Okay, KSEG1 is mapped, but it's uncached. Okay, that means that there's a virtual to a dynamic virtual to physical translation that goes on there. Okay, which means that's done with the kernel's page table. Okay, but it's uncached. Okay, so look at some things that go in the uncached region. I/O. I had input output. I had alluded to the fact that I/O doesn't go through the cache. Okay, because when you write to a particular address location in the I/O region of kernel space, you want that write to directly happen to the next level. And when you read, you want it to be directly reading from that I/O space, because that's the concept of memory mapped I/O, is where we control input-output devices with the memory system. So we read and write to regions of memory within this I/O space, and that causes things to happen. If we put a cache between our processor and the I/O space, we wouldn't get the results that we would expect. We would write something to the cache, and then if it was write back, it wouldn't happen for quite a while. We want it to happen immediately. And likewise, if we read from the cache, we want to be directly reading from the I/O device. We don't want to be reading from a cache. So for input output, it circumvents the caching system. And the way it does that is by mapping I/O into the KSEG1 region, which is uncached. Okay? So I/O devices are there. And then boot ROM. Boot ROM generally is very small and very fast and does not need to be cached. So boot ROM is contained within the KSEG1 region. Okay? And then KSEG2 acts very much like user space, except it's in kernel space, and so it's mapped, which means there's a page table entries keep track of this virtual address space and allow us to map this anywhere within physical address space, and it's cached. Okay, so okay. Hopefully I haven't confused you too much. We'll keep coming back to this diagram as time goes on. Okay, so these page tables again are stored in KSEG2, so the user space page tables are stored in KSEG2. Now, what's interesting is not all of the user page tables can fit in KSEG2, because KSEG2 is well, I mean, how big was it? Let's go back and look at how big it was. Just in this example, right? Oh gosh, I'm going to have to do math here. C is 12. Well, just roughly look at it. It's just based on what it looks like. It looks like it's, maybe, remember this upper half of the kernel space is 2 gigabytes. So it's less than a gigabyte of space, okay? So if every process took 4 megabytes of page table, we would quickly fill up that kernel space. So that's where multi-level page tables come to the rescue. Okay, because if you remember in that user space that I was talking about, the stack and heap grow together, and then you have this giant void. I'm going to make you guys sick going back and forth between these two diagrams. I should have made a slide for this. This giant region here in the middle of kernel space where the stack grows down and the heap grows up, that is a giant void in the virtual address space. And I mean, for simple programs, that void may be almost 2 gigs, and so the program only consumes a few megabytes of memory, and so then it has this huge void of virtual address space that's not even being used. Okay, so if we had a single level page table, we would have to allocate entries in that page table for that that huge void of address space, and that would be inefficient. So that's where multiple level page tables come in. And if this is the graduate class, we would spend a lot more time on this, but unfortunately it's not, and so we just can't spend much time on it on multiple level page tables. If you take an operating systems class, you'll study it. But basically, with multiple levels, we can then make our page table much more efficient, and for the most part, it only maps the used sections of virtual address space. So then, on average, our page tables are much smaller than 4 megabytes. Okay. Okay. All right, swap space. We already talked about this, that an entry could be in physical memory or it could be on disk. And if the valid bit is not asserted, the page is either on disk or does not exist. This is an interesting part. Okay, you know, in Linux you end up with or in Windows you get a segmentation fault, and what that basically means is there was a fault in the virtual memory system, which means you tried to access memory that doesn't even exist. Okay, so when your program goes off on the rails and you get a segmentation fault, it's because it's trying to access memory that doesn't exist, and the operating system is like, oh, wait a minute, hold on here. You know, this memory doesn't even exist. So how does it know that it doesn't exist? Well, it goes to find that entry in the page table. It's not there, so then it goes and it looks and checks to see if that space is even allocated. You know, because it has some mechanism for determining whether it's on disk, and if it's not on disk, then it says, well, that doesn't even exist, and then it throws a segmentation fault. Okay, so a page fault now refers to a situation when a requested disk is not in memory and the OS can retrieve it from swap space. Okay, but a page fault may not necessarily be a bad thing. Okay, it's a bad thing if it goes to try to find it in swap space and it's not there. Then it means you're trying to access memory that doesn't even exist, that wasn't allocated to you. So if you can think about how might a program do that, remember that back to that virtual address diagram that I keep going back to. Okay, that large amount of vast space between stack and heap. Okay, if you go to access somewhere in that vast void, you know, within your user space, it's going to cause a segmentation fault, right? So it's going to cause a page fault because it's not in memory, and then it's going to go and say, well, this memory doesn't even exist. It's not even on disk. Because, you know, in order to use that space, the operating system, like for the heap, the way the heap grows is you actually call malloc, which then malloc calls a routine called sbreak, and sbreak is an operating system routine that then goes and provides your program another section of memory. Okay, so you call malloc. Malloc then calls an operating system uh, call called sbreak, which then goes and actually allocates your program more space. Because what it has to do is it has to go and patch up the page table and everything. And if you try to access a region of memory inside your program without calling malloc first, okay, or you screw up on your pointer math, then you're going to end up causing a page fault. And then that page fault is going to lead to what Windows calls a segmentation fault. I keep mentioning segmentation faults because programmers are very familiar with what that is. So now we're kind of talking about what that actually equates to in the hardware. Okay? Okay, we've seen this diagram. It's a little different now. We take our virtual page number, we use that to access our page table. The page table tells us whether the entry is mapped in physical memory or if it's in disk. So if the valid bit is not asserted, then we have enough information to determine where on disk it actually is. Okay, and then within that, there's some mechanism for the operating system to indicate that no, this is not even this entry doesn't even exist on disk. Okay, and of course a multi-level page table. Real quickly, let's go to the whiteboard here. What it does is it takes Okay, a single level page table takes your page offset, okay, and then it takes the virtual page number, VPN, that's supposed to be a V, by the way, VPN, and it just takes that VPN and uses it to index the page table, which is what we see here, right? Virtual page number indexes page table. Okay, a multi-level page table breaks that virtual page number into multiple chunks. So like Linux uses a 3-level page table, so it's going to take that virtual page number and break it up into chunks, and then the first chunk will index a table that then points to another table, okay? And then the second part of the virtual page number is combined. I need to hold on. I know I normally talk about this in the graduate class, but it's just so interesting to me. Virtual memory is such a fascinating topic. I think I've mentioned that several times. Okay, so okay, all right. Let me see here. Normally I have slides for this in the graduate class, so I'll do it without the slides. So we have a page table register. I was trying to remember what we called that. So we have a page table register. The page table register points to our, okay, that's up here. That points to the start of our first level of page table. Then the first section of our virtual page number points to an entry within that first page table. That entry points to our the base address of our second page table. The second part of the virtual page number is the offset within that page table. And just as you can imagine, that then points to the base address of a third page table, and then, boy, this is really getting nasty, and then the third section of the virtual page number points to an entry within that last page table, and then that entry now points to your physical page number. That actually has the physical page number or the information needed to retrieve it from disk. Okay? And so this seems like it adds more complication and is less efficient, but in the end, because of the fact that most processes don't use nearly their full address space, this actually becomes more efficient because you only map the sections you only have entries for the sections of address that you're using. Okay. Okay. I got to move on before I really confuse the hell out of you. So, okay. So again, we're swapping things between disk and main memory. So the operating system is constantly moving stuff between disk and main memory, or between swap space and main memory. Swapping pages back and forth between disk and physical memory is referred to as thrashing, and it's extremely slow. Okay, this is something that computer users don't really observe that much today, especially as we move to flash devices that don't even use swap space, and as our DRAM becomes so large. But in the older days, like in the 90s, when your computer was just terribly slow and that hard drive light was just constantly blinking, and some computer specialist or somebody who's savvy in computers says, "Oh, that's simple. You just need more RAM." And then so you say, okay, so you go out and you go to Best Buy or somewhere and you buy more RAM, you stuff it in your computer, and then magically it works a hell of a lot faster. Okay? This is why. Your RAM was insufficient compared to what you were trying to do, and so the operating system was continually having to transfer data between your swap space on your hard drive and your physical memory, and that's why the hard drive light was always going. And hard drive access is extremely slow, and so you solved the problem magically by adding more RAM, because now if you doubled your RAM, maybe now your system rarely has to go out to swap space. Okay, so that's how a user observes when you're doing too much thrashing. Okay. And so that's actually what's going on there. Is the operating system is transferring data between the hard drive and physical memory. Okay. Um, so we're spoiled nowadays because even small systems like this have more than enough RAM. Okay, the operating system, again, I mentioned, uses least recently used, just like we did in our cache replacement policies. Okay, and it uses that to determine which blocks to push out to disk. Okay. Okay. Well, if we think about how this virtual memory works, we're probably thinking, man, this is extremely inefficient. Because now I'm telling you that in order to do a virtual to physical address translation, we have to we have to perform an additional read in memory if it's a single level page table, and if it's a multi-level page table, we have to do n additional reads where n is the number of levels in our page table. So in my example over here where we have a Linux system, wow, that looks really bad, that has 3 levels of page tables, we have to do one, two, three reads from memory just to translate an address. Okay? So that just wouldn't work if we didn't get some help from the hardware. Okay? That just would not work. Every address translation requires 3 additional reads from memory, in addition to the one read that you're actually trying to do. Okay? We would never get anything done if we didn't have assistance from the operating system. So what we would like is a way to cache the oh, this is a mistake in my slides. I need to fix this. We want a way to cache the most recently used portions of the page table. Okay? So we want a hardware mechanism that caches the most recently used portions of our page table. If we can cache the most recently used portions of our page table, then and we don't have to go out to the page table for every translation, and that will drastically improve our performance. And then the only time we have to go out to the page table is when the page the translation that we're looking for is not in this special cache. Okay, I need to fix those slides. That should be most recently used portion of the page table. Okay. All right, so here's what it looks like. So spoiler alert, this special cache is called a TLB. It's a translation look-aside buffer. Now, remember I mentioned that virtual memory is one of the oldest concepts in computer design, and of course the most fascinating, one of the most fascinating. Well, it turns out that the old term they used to use for caches was translation look-aside buffer. Okay, but then when we started using caches for data, they came up with the term cache, which is a much easier term. But then they kept the translation look-aside buffer term for the virtual memory system. Okay. So you're going to see that this TLB very much resembles a cache that we already talked about. Okay, but it's not caching data; it's caching address translations or page table entries, essentially. Okay, it's essentially a cache for the page table, a special cache. Okay, and as we'll see in later diagrams, accessing the TLB happens in parallel with the cache. Okay, and I'll show you how that works. Okay, so most of the time we go and we access a virtual we feed our virtual page number into this TLB, and then most of the time the virtual page number is going to hit in the TLB, okay, and then provide a physical page number, okay, which they say physical address, but it's basically a physical page number, which the physical page number is then combined with the page offset to create a physical address, and then that is then accessed, allows us then to access that particular location in physical memory. Okay. Now you're probably wondering, well, where does the data cache and instruction caches fit into this? Well, not yet. I'll show you in a bit. this diagram does not show how that fits in. Just add too much complication at once. Okay, so most of the time, 99% of the time, or 99.9% of the time, the translation that we're looking for is actually in this TLB. So we make the TLB large enough to reduce the miss rate to the point where we actually this virtual memory system runs quite well. Okay. So our virtual page number is fed to the TLB. If there's a hit in the TLB, then we grab that physical page number, combine it with the page offset, and we've got our physical address. Okay, and then we can go and access memory with that physical address. If we miss in the TLB, then we go and it actually invokes the operating system, and the operating system then goes and looks up this entry in the page table, and then what it will do is it will go ahead and evict an entry from the TLB and replace it with with this entry, because now the virtual page number that we just requested is now the most recently used. Okay. And of course we still might have things on disk, so I've got a table in the slides that kind of show this. We can have a miss in the TLB and a miss in the page table, in which case we need to go, and that page is not on in physical memory, so we need to pull it from disk. We need to update the entry in the physical page number, and we need to put that entry into the TLB. Okay, so there's a lot of things at play here. Okay. So translation look-aside buffer is a small cache, typically with a high amount of associativity. In fact, oftentimes it's fully associative. Okay, so in this case, we have a tag. Notice we have a tag, and there may not be an index, because remember that's the way physically or fully associative caches work. There may not be an index. We have a tag, and each tag in our TLB has a comparator, and we present the TLB with this virtual page number, and each comparator checks its tag to see if there's a match. And again, we design it so that there's only ever one entry that it will hit on in the TLB. Okay, so it's typically a fully associative cache. Okay, unlike the caching system, the data cache and instruction cache that we've talked about so far, this is managed by the operating system. So the operating system is actually what refills the TLB. Okay, so when we miss in the TLB, we invoke the operating system through the exception mechanism. Okay, remember when I talked about exceptions, I said that there are some exceptions for virtual memory that happen quite often. This is an example. A TLB miss causes a special exception that invokes the operating system, and then the operating system goes in and refills the TLB. Okay, and it references the page table to refill the TLB. Now, of course, you can have a miss in the TLB, a miss in the page table, and then which would be a page fault, and then you have it may be on disk, or it doesn't even exist, in which case then the operating system is going to terminate your program and send the user a nasty message. Okay. Okay, more characteristics of a TLB. How large is it? Well, for smaller processors, it might only be 16 entries. For larger processors, it could be up to 512 entries. And guess what? Higher performance processors like the i7 have a 2-level TLB system, just like we do in cache. So they might have 3 levels of cache and 2 levels of TLB. And so they'll have a very small TLB that's very fast to access. Then they'll have a second larger TLB, and then finally, if you miss in the second larger TLB, then you have to go to the page table. And Intel processors take it even further, and they have a hardware mechanism called a page table walker that actually walks the page table for the operating system and will actually retrieve that entry for the operating system. So a lot of that even happens in hardware. Actually refilling a TLB on a higher performance x86 processor, for example, will happen almost completely in hardware. Now the operating system still controls that. Okay, so the operating system is still heavily involved, but there's this page table walker that speeds up the access of the page table. So, okay, block size, you might have 1 to 2 page table entries. Okay, and the hit time is a half to 1 cycle. Okay, So it has to be very fast. And we're going to see a diagram here shortly that shows how it integrates into the level 1 cache. So it's an integral part of the level 1 cache and caching system, as we'll see in a minute. And so it has to be fast, which is why higher performance processors have multiple levels of page tables, okay, or of TLBs. The miss rate is very low. Okay, we're talking. I mean, 1% would be terrible performance. Uh, More likely, it's a tenth or a hundredth of a percent miss rate. Okay, so we make the TLB large enough that we rarely miss, because a miss, as we're going to see, a miss penalty could be anywhere from 10 cycles all the way up to millions of cycles if we have to go grab it from disk. Okay. And the block replacement strategy that's typically used is for a TLB is random. Uh, we could come up with a least recently used is used for the page table, but that's because when the page table is being accessed, the operating system has a lot more time to, especially when there's a miss in the page table, then it's going to go out and access disk, so it has a lot of time to actually update this least recently used algorithm. The TLB is still very fast, and TLB misses are still handled very quickly, and so least recently used is still quite a burden for the TLB. Not so much for the page table, because when we go out to disk, I mean, it's going to take millions of cycles for the disk to grab the data we want, so we've got nothing but time to update these least recently used algorithms. But when we're refilling a TLB, we want that to be as fast as possible. So it turns out we generally use a random replacement strategy for the TLB. And as I mentioned, it's tightly integrated in the cache. So let's look at an example of how it's tightly integrated into the cache. So this is a 32-bit address space. This is that Intrinsity fast math processor, the real world processor, okay, that supports 4 kilobyte pages. Okay, it has a TLB that's 16 entries and it's fully associative. A shared TLB. Okay, just like in the cache system where we can have a split level 1 and a split level 2, we can have a split level 1 where we have an instruction and data cache. We don't really have split level 2s. We can have a split TLB. So we can have an instruction TLB and a data TLB. So sometimes some processors will have a split level 1 cache, but then a unified or shared TLB. Okay, or they'll have a split level 1 cache and a split TLB. So they'll have a TLB for instructions and a TLB for data. Okay. Sometimes they'll have a little buffer for the instruction TLB, because of the smaller size that instructions take up. They generally don't need as large of a TLB as the data side of things. Okay. All right. So then we have 64-bit entries for virtual page number and physical page number, valid bit, dirty bit, and all that. So each TLB has 64-bit entry. We have a 20-bit virtual page number and 20-bit physical page number. Okay. All right. Here's what it looks like. Okay. This is integrated with our data cache. This is integrating a TLB with a data cache. Okay, so here we have our virtual address space, our virtual address, which again the processor is only sees virtual addresses. At the processor level, it only sees virtual addresses. Okay, so we take the page offset, okay, and we translate this into a physical address. So the page offset, as I mentioned, just directly transfers. Okay, and then the virtual page number we then feed into our TLB, and we use that. And notice, look, each tag has its own comparator because this is a fully associative TLB. So one of these tags, it happens to be this one, has a hit. Okay, that provides us then a physical page number, which is then fed down in here, and then that's used for the rest of our cache. So this is an example of, well, I'm not going to confuse you anymore. So let's just keep going, and then I'll talk about that in a little bit. Okay. So then now here's where, remember we talked about how we broke up the address for the cache, where we broke it up into a byte offset, a block offset, a cache index, and a physical tag. Now here's where all that comes together. See, so we break up in the memory hierarchy, we break up the address into several parts in different portions of the memory hierarchy. So when we access the TLB, we break it up into page offset and virtual page number. That allows us to then translate into a physical address, and then from there, we go ahead and we then further break up that physical address into portions that will then allow us to access the cache. Okay? In the early MIPS processors, the TLB access would happen one cycle before the cache access. So we actually required, we had a 5-stage pipeline, but they figured out a way to have to access the TLB one cycle ahead of the cache access. Okay, so I had some more slides on this later on down the way, but we're just not going to get to them this semester, unfortunately. So again, we go ahead and in this example, we have virtual. We're in the virtual address space, and then here we're in the physical address space, okay? And so this is a physically addressed cache, okay? This is a physically addressed cache. So because what we do is we actually, in one step, we translate the virtual address to a physical address, and then in the next step, we access the cache. And so when we access the cache, we're presenting the cache a physical address, okay? Now, in the graduate class, we spend a lot more time on this, and we actually talk about how to actually make our cache virtually addressed. Okay. The problem with the cache being physically addressed is we have to access the TLB and the cache sequentially. We have to first access the TLB to do our virtual to physical address translation, and then we have to access the cache. And so we have to go from physical. We then, once we have a physical address, then we go to access the cache. So physically addressed caches can be a performance limitation, but they are overall more simple. Modern processors actually use what's called virtually indexed physically tagged caches, where the TLB and the cache can actually be accessed simultaneously. Okay, so that's a real mind fuck, I tell you. So we just don't have time to get into it in this class. So note that the example I gave you, the cache is physically addressed, but there are other systems that either the cache is virtually addressed or it's virtually indexed and physically addressed. Most modern systems are virtually indexed, physically tagged caching systems. Okay, because there's a whole bag of issues that go along with a virtually addressed cache that I don't have time to get into. And physically addressed caches are just performance limiting. But the early 80s processors were physically addressed caches. Okay, a TLB miss. And holy crap, we're over time, so I'm pretty sure we're quite a bit over time. So I'm just gonna kind of keep going for a little bit. I haven't even given you all a quiz or anything. So let's have a quiz here. Okay, describe the function of the TLB, the translation look-aside buffer. What does the TLB do for us? And really, this diagram kind of helps you understand that. Okay, why do we need a TLB? Okay, let's see. What other question could I have you ask? What's the purpose of the page table in the virtual memory system? What does the page table do for us? Okay, and then finally define swap space. Okay. All right, you may have to go back and look at some of. You may have to go back and read some of or watch some of the lecture to answer these questions. So, okay. All right, let's real quickly talk about how a TLB miss is handled, and I think we're gonna have to call it. Unfortunately, that's pretty discouraging for me. There's so much more fun material to cover here. So, okay, all right. So a TLB miss happens when a virtual page number is not found in the TLB. Okay. So just like we had a level 1 or a level 2 cache miss, we can have a TLB miss. Okay, and TLB is a fully associative cache, which helps reduce the miss rate significantly, and we try to make the TLB large enough so we don't have a lot of miss rate. But when we do have a miss, we want to make it as fast as possible, the handling of it. Okay, so as a result, the TLB, when we have a TLB miss, it vectors to its own special address location. And I mentioned earlier when we talked about exceptions that you have kind of these special exception addresses for virtual memory, and that's what we have here. And the reason you want to vector to a very special address is because you don't want the processor to have to take time looking at the cause register and figuring out what actually caused the exception. No, you don't. You want it to immediately head to the TLB miss handler, because this is, it's an actual software construct, and you want that to happen as fast as possible. Okay? So it's part of the operating system, and it vectors to its own special location. It vectors to the unmapped region of kernel space. And the reason it vectors to the unmapped region of kernel space is because you don't want to be handling a user space TLB miss and then get a kernel space TLB miss at the same time. That will be a mess. So the way they avoid that is that's why they have that special section in kernel space, and it's a small section that is unmapped. So when you vector to that section in kernel space, you cannot get a TLB miss exception. Okay, and in fact, interrupts are turned off when it reaches that section, and so the idea is you cannot have a nested exception happen in that critical section of code. So let's go back to that diagram that I keep looking at. So again, we're talking about kseg0, which is an unmapped section, and that's the exception entry points. So all exceptions vector to somewhere in that region. If it's a TLB miss, it has its own address in that, but it's still in that region. Okay, so that means that the processor can immediately start refilling the TLB without trying to triage the exception. Now, all other exceptions vector to a different location, and those are a little slower and less critical. And so the first thing the exception handler has to do is it has to triage that exception, look at the cause register, figure out what caused it, so on and so forth. But for a TLB miss, that does not happen. The TLB miss goes to a very special location inside that region of memory, and that allows it to quickly start handling a TLB miss. Okay? Now, again, I want to point out that that's part of the operating system, because if we go back and look at that diagram, that's happening within kernel space. So whenever an exception is invoked, we're now in kernel space, and we're now invoking a portion of the operating system. Okay? All right. The fast math processor, assuming there's no cache misses when it's handling the TLB miss, which you could have a cache miss when handling the TLB. I got a table that shows all of that. It takes only 13 cycles to refill the TLB. Okay, so it's a very fast refill, and I believe I have some example code of what a TLB miss handler might look like. Okay, and so what it has to do is it has to inside that TLB handler, it has to quickly access the page table. Okay, and we use the write back policy to update. It has a dirty bit and access bit, so it retrieves those access bits and whatnot, and then it goes and it refills the entry in the TLB. So all it's doing is accessing the page table and putting that page table entry into the TLB, and then of course it has to handle evicting a entry in the TLB. So it may have to take an entry in the TLB and update that entry in the page table if some of the flag bits were changed. Okay, so 13 cycles. It can access the page table and refill the TLB in 13 cycles, assuming no cache miss. We could have a cache miss, and of course you know cache misses could take hundreds of cycles if it has to go all the way up to main memory. Okay, but if that page table is cached, if that page table happens to be in cache, we can refill in 13 cycles. Okay, this is a fun chart. Let's just go through this real quickly. It looks like a confusing mess, but it's actually not too bad. Okay, so we start with a virtual address. We access the TLB. Is it a TLB hit or miss? Okay, if the TLB does not hit, then we have a TLB miss, and we go ahead and invoke that exception handler and refill the TLB. Okay, if it's a TLB hit, then yes, we have a physical address. Are we writing? No, that's a little easier. I mean, reading is easier than writing. So if we're not writing, then we go down here and try to read data from the cache. Okay. Well, just like we talked about, is it a cache hit or a cache miss? If it's a cache hit, we're done. Deliver data to the processor. We're done. So that's the fast path. Okay, right here. This is our fast path. This is the way we want things to happen most of the time. Okay. Well, let's look at this. If it's a cache miss, we know what happens, right? If it's a cache miss, the cache will go out and retrieve that data, and so then we go here, right? So try to read data from the cache. Is it a cache hit? No. Cache miss. Stall the processor, read the data, then come back and read the data once the cache retrieves the data from the next level. Then we'll come over here. It'll be a cache hit, and we deliver data to the processor. Okay. All right. Let's go down this leg. All right. So physical address. There was a TLB hit, and we are writing. Okay. Writing has special access. Is the write access bit on? Okay. This is where our virtual memory system provides write protection. Okay. So what we're saying is, are we even allowed to write to this region of memory? If no, well, now the operating system is invoked, and we say, hey, there's a problem here. We're trying to write to data that's read-only. Okay, so there's a write protection exception. Okay, all right. If the write access bit is on, then this is like we talked about in the earlier parts of Chapter 5. It's now, then we go to access the cache. Okay. So is it a cache hit? If it's no, we go ahead and and again, that depends whether it's write allocate or write no allocate strategy. In this case, it's a write allocate strategy. So then if there's a cache miss, then we go ahead and we stall the processor, read the block into cache, and then go and try to write to it again. Okay? And then once it's a cache hit, then boom, we're done. Write the data into the cache and update the dirty bit in the TLB. And the dirty bit in the TLB says that particular page has been modified. So if we have to transfer it back to disk, it means we have to actually write the data from physical memory to disk. Okay. If the dirty bit is not asserted, then if we're swapping out a page from main memory, then we just erase it. We just overwrite it. Okay. Okay. See, so we went through that table. Not too bad, right? Now sometimes the operating system, actually, I think this is the way Linux does it, is it actually uses the write protection bit to allow it to update the dirty bit. And so I talk about this a little bit more in the graduate class. Basically what it'll do is it'll initially set the write protection bit to 0 in the TLB, and so as long as you're reading, everything's happy. But then as soon as you go to write to a particular page, then you'll actually invoke this write protection. Let me erase some of this stuff so I can explain this a little bit. Okay. So what'll happen is the TLB write bit will initially be set to 0. Okay. Even if the page table entry says that you can write to this to this particular page. Okay, this is how it maintains the dirty bit. So what'll happen is you'll go down this path, you'll have a TLB hit, and then the write access bit will be off. So you'll say you'll go down this path. No. And you'll trigger an exception. Okay? So then what the operating system will do is it will go and reference the page table and check to see if we're even allowed to write to this particular page. And if we are, it's at that point when it'll actually write the dirty bit. So then it asserts the dirty bit in the page table, and then it goes and it updates the TLB entry and allows write access to happen. Okay? So sometimes the operating system has to do that if the TLB itself does not maintain a dirty bit. So we don't actually have to maintain a dirty bit in the TLB. We can actually just maintain a valid bit in the TLB, and then that through that write privileged bit, that write privileged bit, we can then maintain the function of the dirty bit as well. So I realize that's probably pretty confusing. If you have any questions, bring them up on the discussion board. Email me. I'd be happy to try to explain it. Okay, we're gonna have to call it here in a little bit. So I'm gonna go a little bit longer. I apologize. This is gonna be a long lecture. It's the last one. So, Okay. We can have a number of combination of events happen here now that we have a TLB, we have a cache, and we have a page table. Oh, and I want to point out that this specific flow chart is for the data access. Okay. The cache access, the instruction access rather, is very similar, except with a cache, we can't actually write to an instruction cache. So this whole portion is gone, right? We don't even have this block. Okay? So but the question is that section of memory executable? There's a protection bit that indicates whether we can actually execute from that portion of memory. And so the instruction cache or the TLB is going to cause an exception if we try to access a portion of our memory that's not marked as executable. Okay, and that provides a level of protection where user programs, if they don't sanitize their input, nefarious users could insert in their input code, and magically there's some. I've seen it done. It's amazing how you can do this. People are very clever. They can actually, as part of their input, like let's say it's asking for your name. If the program doesn't sanitize the input properly, and it allows an overrun to happen, okay, somebody could go ahead and put in a very long name, and then at the end of that name they could put code, and then magically get that program to execute the code. It's phenomenal. Well, so that protection mechanism attempts to protect you from that happening. So data is treated as data, and it cannot be executed unless it's explicitly marked for execution. So if you take a security class, they will show you how to do these different attacks. It is amazing. And I would recommend everybody in computer engineering take a class like that, even if you're on the hardware side, because there's all kinds of crazy attacks that can be done in hardware because of this. But in software, there is a huge attack field there that's available, and so it's just fascinating. The hardware side, you have to worry about weird things like side channel attacks and stuff like that. So we spent a lot of time studying those. In fact, Jim Pasqualik, a lot of you probably know Jim. He's a great professor. His research is in side channel attacks. So from the hardware side, and he's actually very involved in HOST, hardware-oriented security and trust. It's a conference that I think he's a co-founder on. And anyway, they look at security from the hardware perspective. So from a hardware engineer, definitely recommend you take Jim's class. But for software, if you're software on the software side of things, there's a whole bunch of classes offered in the computer science department that will show you how attackers can infiltrate your code. And it's really good. It's really good for you to understand if you're writing programs to understand that. Okay, all right, that's a tangent as is most of my lectures. So, all right, so let's look at these things, how they can happen in concert. So we can have a TLB hit, a page table hit, and a cache miss. Okay. Now, the little note here says, well, yes, it's possible, although the page table is never really checked. If the TLB hits, we assume the entry is in the page table. And remember, we talked about this term in caching. That means that there's an exclusive or inclusive relationship between the TLB and the page table. The TLB will always be a subset of the page table. If an entry is not in the page table, it cannot be in the TLB. Okay? Which we can immediately eliminate one of these here, right here. I'm just going to cross this line out. Okay, see how we have a hit in the TLB and a miss in the page table? That can't happen. Okay, neither can this. These are impossible because the TLB is always a subset of the page table. It's inclusive, to use our earlier caching terms. Okay, so we can have a hit in the TLB, and that indicates that there's a hit in the page table. But again, remember, if we hit in the TLB, we don't access the page table, and we can have a miss in the cache. So that actually happens quite often because the miss rate for the TLB is much lower than the miss rate of a cache. So quite often we will have a hit in the TLB and a miss in the cache. Okay. Now we can have a miss in the TLB, a hit in the page table, and a hit in the cache. That's kind of interesting, but it can happen. So, because the TLB and the cache somewhat act independent of each other, okay, and they have obviously different characteristics, we can actually have a miss in the TLB, a hit in the page table, and a hit in the cache. Okay? So we can also have a miss in the TLB, a hit in the page table, and a miss in the cache. Okay? So you remember our little flow chart that we looked at. Whoops, it's right here. Okay? We could go down this path. Okay? So we go down here and boom, there's a miss in the TLB. We cause a TLB exception. The operating system goes and refills the TLB. So then we start back up here. There should be a arrow going back because the operating system will refill and then we'll start over again. Okay, because in the TLB exception handler, and I talk about this a little bit later, we refill the TLB and then we go and we invoke an ERET exception return instruction that then causes us to return to the location that the EPC was pointing to, which will be the offending instruction that caused the TLB miss. So we're going to re-execute that instruction that caused the TLB miss, which is either an instruction if it caused an instruction TLB miss, or it could be a load word if it caused a data TLB miss. So we're going to re-execute that instruction. So after we refill the TLB, we're going to re-execute that instruction. So now we're going to have a hit in the TLB, but then, and let's just say we're writing, then we may have a miss in the cache, and then the cache has to go and refill, and then finally we'll get a hit. So it's a very torturous path. Okay, you're probably wondering at this point, it's amazing that memory hierarchies work as efficiently as they do, and they work very well, but it is amazing that they do work like that. Okay, so we can have a miss in the TLB, a hit in the page table, and a miss in the cache. We can also have a miss in the TLB, a miss in the page table, and a miss in the cache. Okay, that's a real torturous path. So when we miss in the page table, and that's not reflected in this diagram, but when we miss in the page table, we then have to go back out to disk. Okay, so that's in this diagram, right? So we're gonna miss in the TLB. We're going to miss in the page table, which means the valid bit is 0. We're going to go to disk, which means we're going to then have to swap, okay, an entry. Well, I don't know why I'm going to different entries here. We're going to have to do this, something like that. So we're going to have to pull a page out of memory, put it back into disk, and then pull a new entry from disk and put it into physical memory. We're going to have to then go and update the page table entry and then update the TLB. And here's what's funny, operating systems actually they update the TLB in a separate step a lot of times. What they'll do is when they have a page fault, they'll go and put it into physical memory and update the page table and then return from that exception. I know, they do this, it's crazy. Then what they'll do is it'll re-execute that instruction. Now it's going to cause a TLB miss, but then it'll use the TLB miss handler to do that, and that's going to be a lot faster. So it allows them to not have to duplicate the TLB miss handler code, and it only adds a few clock cycles actually. So yeah, what it'll do is it'll actually do that in separate steps. So when it encounters a page table fault, it'll go and it will swap that page from disk from disk into memory, and then it will re-execute that instruction, and then it'll come through and cause a TLB miss, and then it'll go ahead and handle the TLB miss in the fast TLB miss handler. And of course now we know that the page entry is going to be in the page table because we handled that page fault. Okay. All right. Fun stuff. Fun stuff. Okay. I crossed those out because we can't even have those. So then the next one that we want to look at is, can we have a miss in the page table, or a TLB, a miss in the page table and a hit in the cache? And the answer is no. And let's talk about why. Okay. What this is indicating is that we have a piece of data that's in the cache, but it's not in physical memory. We can't have that, okay? Because we said that cache is inclusive, okay, to the physical memory. So the cache is a subset of the physical memory. And so if we have a page table miss, it means that that entry is not in the physical memory, which means we cannot have a hit in the cache. So this one's impossible as well. These last three are impossible, okay? And so we can only have these upper four. Okay. All right. Additional support for virtual memory. I mentioned that we have this concept of user and kernel mode, and that's extremely important. So we have to have user space and we have kernel space, and we have privileged instructions that can only be executed when in kernel mode. So we have to keep track of a mode bit. And the way we delineate between being in kernel space or in kernel mode and user mode is when we encounter an exception. So when we encounter an exception, we vector to a particular location in kernel space, and that mode bit is switched. So now we're now operating in kernel mode when we encounter an exception. And remember, a syscall and a break is a special type of exception that the user can actually invoke. So if the user needs attention from the operating system, for example, if it wants to write to a I/O device, it will invoke a syscall, and so the user will then will then invoke an exception. Okay, and then that mode bit will be switched. It'll vector to a special location in memory in kernel space. The kernel will then look at the argument registers and figure out what exactly. Well, it'll figure out that it's a syscall, and then it'll look at the argument registers to figure out what exactly the user wanted. Okay, and that's how that coordination between user and kernel works. So whenever a program needs attention from the operating system, it'll do so through a syscall. Okay. And of course the TLB, there has to be instructions and registers, special instructions and registers that allow modification of the TLB. So that's what the operating system uses to maintain the TLB, those are privileged instructions, okay, which means that you have to be in kernel mode to try to invoke those instructions. If you try to execute a privileged mode instruction when in user mode, it will cause an exception, and then the operating system will basically shut your program off, okay? Um, Again, we have that unmapped address region in kernel space, and that's where exceptions vector. And there also has to be a way to enable and disable interrupts. Okay. So if we go back to this, we have this kseg0 section. That's our exception entry point. And again, we have multiple exception vectors. You know, a special one for handling TLB misses, and then there's a special one for reset and all of that. Actually, reset vectors up to the boot, the kseg1 area, but that's another discussion. Okay, so okay, so those are the things that we need. These are some registers that are used for maintaining the TLB, and again, this is very MIPS specific. So we have the EPC, we remember that, the error program counter, the cause register. Those are used for any kind of exception, okay? But they're also used for refilling the TLB and whatnot. Then we have this bad V address, so bad virtual address. If a TLB exception is caused, that the address of that caused that exception is stowed away in this bad virtual address. And that allows the mishandler, the TLB mishandler, to quickly handle that miss. The index is a location that the operating system writes to this address, and that then tells it which TLB entry it's attempting to modify. Random is just a free running counter that the operating system uses to determine which TLB entry to evict. Okay, entry low and entry high are because each entry takes up to 64 bits of space. Then entry low and entry high are portions of the TLB. The entry low is the physical address, and so you can think of that as the data inside the TLB, and then the entry high is the virtual page address. That's the tag, okay, of the TLB. And then you have this context register, which is again used to aid in TLB refilling. It actually stows away the page table address of the particular application or process that caused the TLB. Okay, let's talk about the TLB mishandler. It's located at a special address dedicated for this purpose. That makes it fast. Okay, we have a TLB write instruction. It's a special instruction that allows us the operating system to modify the TLB. Okay, so we use that in conjunction with the entry low, entry high, and the index, and the random. Okay, so TLB write loads entry low, entry high contents into the TLB at a location pointed to by random. Okay, and entry low is the page table entry, and entry high is the virtual page number, which is essentially the tag for the TLB. I realize I'm going through this very quickly because I'm way out of time here. Okay, so this is an example TLB handler, and so I'm not going to go into detail because we just don't have time. But you can see that, what is it? 1, 2, 3, 4, 5. If you have a single level page table, you can handle a TLB miss in 5 instructions. Okay, now that's a big if, that's a huge caveat, because the Linux kernel, for example, its TLB mishandler will look a lot more complicated than this. Not a lot more, but a little bit more complicated, because it has a 3-level page table. So it can't quite use all of these little features that MIPS built in, because it has a more complicated page table. So all these little cute features that MIPS built into their instruction set architecture in the 80s is useful if you have a single level page table. So for a very small embedded system these days, it may be useful, but for everything else, you have to. There's a lot more work that has to be done. The other thing I want to mention, the context register is populated with the application space ID. That is the process ID. Okay, because we have multiple processes, we have to keep track of um, not only what's the virtual address, but what address space did this come from? Because again, process 0 and process 1 will have common virtual addresses, right? Because their virtual address space looks the same. But, you know, 0x000 in process 0's user space is different than 0000 in process 1's user space. So the difference is now the application space ID. So you have the application space ID keeps track of which user space you're actually referencing. Okay? And then the virtual address tells you within that user space where are you referencing. Okay? All right. Yeah, so I already talked about that. Context switches happen a lot. So context switch is when a process or a processor stops executing a given process and goes and starts executing another process. Well, if you didn't keep track of the application space ID in your TLB, you would have to flush the TLB on every context switch. And that would be terribly inefficient because context switches happen every few milliseconds. So the TLB is designed to actually support multiple processes happening at once. Okay, so multiple processes can reside inside the TLB, and the way they do that is with that application space ID. Again, some hardware and some operating systems will call that the process ID, but they're synonymous. Okay. It was just an earlier term. Okay, this is where the K0 and K1 registers are used. If you went back and looked at that mishandler, you would see that they used K0 and K1. Those are our general. There are two registers from our general purpose register, and convention says don't touch those because the operating system needs them. That's what the operating system uses them for. Okay, and again, the Linux mishandler is a little more complicated because it has a 3-level page table. So without cache misses, the Linux mishandler can actually execute in about 20 cycles. And if you want to look at what that looks like, you can go look at the CMIPS runbook, and it will actually show you what the Linux TLB mishandler looks like on a MIPS machine. Okay, and so it makes use of the context and bad V address registers, and in about 20 cycles it can refill a miss. So it's not too far off from the single level page table that could be accessed in about 13 cycles. So add another 7. Okay? That's this unmapped address region. I've talked about that quite a bit. The reason we have to have it unmapped, just to reiterate, is because when we're handling an exception, we don't want to have a TLB exception happen from the operating system. So that's why we don't. It's an unmapped region, which means it's a very trivial mapping from virtual address to physical address, and so we cannot have a TLB miss when we're accessing data within that KSEG0, that unmapped region. Okay, and the exception entry points start at that unmapped region. Okay, I have to stop here. I could keep going, but honestly, I really need to stop here. So if I have some time, maybe I'll put out an extra lecture. Otherwise, hopefully you're getting plenty out of this. It's been a great semester, even in the midst of this pandemic. I hope you've been enjoying these lectures. I don't know if evaluations, I can't remember when they closed. They may be closed now. Hopefully you had time to fill out an evaluation. If you don't, you can always email me with suggestions and whatnot. And so I know there's been a couple of suggestions. Some of them I've been able to fulfill, some I haven't, and I do plan to fulfill them in the future. So I do appreciate those suggestions, even if I wasn't able to carry them out. So anyway, again, it's been a good semester, and we'll stay in touch till the end there. And then, of course, you can always email me later on if you ever have any questions. I have students that I actually stay friends with a lot of my students, and they'll contact me for random questions or just random, hey, look what I did, and so that's always fun. It's very rewarding for me. So anyway, all right. Hope you're all healthy and happy. I'll possibly talk to you later.